like a lot of criteria. It has satisfied closure under addition, closure under multiplication, and plus 8 other properties, right? But when you have to show that some subset is a subspace, we do not have to go verify all the 8 properties for the 2 properties to show that it's a vector space. We only need to prove that it has satisfied the first 2 properties. Other 8, it follows automatically because it still is just a subset of R3. So R3 is a vector space, so R3 satisfies those 8 criteria. So any sub-collection of that will satisfy the 8 criteria. Right? So we just need to show. So we just need to show that LS is closed under addition and scalar multiplication. Want to do it? Take 2 arbitrary vectors in LS, show that their addition is again a vector in LS, and take an arbitrary vector in LS, take an alpha to be arbitrary scalar, so that alpha v is again in LS. Good. Alright, you can tell me the first one. So let's say V1 and V2 belong to LS. Okay, and let's say S is collection of n vectors. V1, V2, Vn. Okay. First case, let's not say V1 and V2, something arbitrary, other than let's say W1, W2. Let W1 and W2 belong to some arbitrary element in LS. And what's our aim? First, our aim is to show that even W1 plus W2 is an LS. Correct? So our aim is to show that W1 plus W2 belong to LS. Now, if you want to show that W1 and W2 belongs to LS, what do you have to show? So we have to show that W1 and W plus W2 is again can be written as a linear combination of V2 Vn. Correct? And we can do that easily because we know that W1 and W2 are belong to the LFS. So yeah. Right. That's nice. That's nice. Here. So what do we have? So we have from this we have W1 belongs to LS, therefore W1 can be written as alpha 1 V1 plus alpha 2 V2 plus alpha n m Vn. Again, since W2 belongs to the LFS, therefore W2 can be written as some linear combination of Vn, right? So W2 also can be written as, let's call it beta. Beta 1 V1 plus beta 2 V2. So beta m Vn. Right? Now we have to, so we know that the V1 is a linear combination of VI, V2 is a linear combination of VI, and eventually our aim is to prove that the W1 plus W2 is a linear combination of VI. And the straightforward thing which we do would be just add them together and hope for the best. So therefore, what do we have? W1 plus W2. A lot of things are going on here, right? So W1 plus W2 means I'm adding this plus this whole chunk, right? So we are using commutative of the vectors. I can switch this addition with this, and I can commutating, and somehow I'm bringing this thing here, right? And then after that, I'm pulling out V1 from that. So I'm using the commutative theorem of vector addition, distributivity with respect to the alpha. So eventually, everything nice happens, and eventually I can write this as alpha 1 plus beta 1 V1 all the way to alpha m plus beta m Vm, and thus I know this is clearly in the linear span of f, right? Why? Because W1 plus W2 is written as linear combination of Vi, correct? And we have to show something else. Let's make this a little bit smaller. Does Lawrence know that we are already class? Right? And similarly, we have to prove that given W1 belongs to, let's just say W, that W belongs to L of S, and alpha is some scalar. We have to show that alpha times W belongs to L of S. Essentially, what we have to show that even alpha times W can be written as linear combination of Vi, right? And that's very trivial, right? The W belongs to L of S, therefore W is alpha 1 or V1 plus alpha 2 V2 blah blah blah, so alpha m Vm, and then you multiply alpha on both sides, use the distributivity of multiplication, scalar multiplication in vector space, and eventually distribute this alpha to everything. We eventually have alpha W is alpha 1 V1 plus alpha 2 V2, so all the way to alpha m Vn. Okay, and that clearly belongs to L. Alright. Now, we are not emphasizing this earlier, but the convention is that we always want our subspace to be a non-integer. Right? So even if we can take an Rm, we can look at the empty set. It satisfies that property under its closed under addition. Is everybody convinced with that? Why empty set is closed under addition? Why? No, when I say empty, it does not even contain 0. This is not violate any of the, because we need to show that if V1 plus V2 do not belong, because we cannot specify any case. Right, so it's vacuously in the sense that I cannot find any pair of V1 and V2 which violates the law. I cannot find any V1 and V2 because there's nothing in it. Right, so empty set so far, what you're saying, so far does satisfy the properties we need to call an empty set of subspace, but we will not. Right? So in vector space, we always want our subspaces to be non-empty. So the smallest you can go is say the zero vector, right? Origin. So we will from now on we will always in addition to showing that it's a closed under addition and scalar multiplication, we will also talk about we will have to show that the L of S or some whatever thing we are trying to show is a subspace, it has to be non-empty. Alright, so we still addition thing we need also need to prove okay. Also need to show that Ls is non-empty. There's origin and so V is origin, right? So if V1 is in there, then 1 times V is in there, right? Because I'm doing all alpha times, so I can do alpha as 1, 2, 3, whatever. So if V is in there, alpha times V is in there. So S is there, so S is definitely in my space. So I have empty. So S, which is not empty, is subspace of subset of subset of, right? Therefore, this is not equal to M. Correct? And okay, one thing I was there in the last page. When you're talking about the linear span of vectors, so if S is any n vector, when you're talking about linear span of vectors, then F need not be independent. So I can just take any arbitrary collection of vectors, we want to 100, 1000, whatever, and those necessarily does not have to be linearly independent. So let's come to this point making the point that I can take linear span of any vector, not necessarily independent. And for now, for your case, it's not very important, but in theory, S can be infinite too. So S can be an infinite set. And it has certain meaning that if it's infinite, what do we mean by alpha 1 v1 plus alpha 2 v2 till infinite sum? So it has a meaning, but let's not go into that.